Let us now proceed to part 3. The next topic is regarding the Bayes theorem and branch probabilities. The Bayes theorem should be studied because sometimes the posterior probabilities and marginal probabilities are not given. Sometimes the problem will only give us the prior probabilities and conditional probabilities. Now, if we're going to compare posterior versus conditional probabilities, let us look at this one and this one. So, for the posterior probabilities, this is read as the probability of S1 occurring given a favorable market research. However, if we look at the conditional probabilities, this is read as the probability of having a favorable research given S1. If this happens, we have to convert the conditional probabilities and change it to posterior probabilities because we cannot perform decision analysis using sample information without having the posterior and marginal probabilities. The Bayes theorem, Bayesian inference, or Bayes rule allows the manipulation of conditional probabilities and change it to posterior probabilities. It was developed by Reverend Thomas Bayes, where you can change the probability of B occurring given A to probability of A occurring given B. If we have knowledge of sample or survey information, then we can revise the probability estimates for the states of nature. Remember, for the PDC problem, if there is no market research or knowledge of sample information, the probabilities are called prior probabilities. Once again, let me reiterate that if we are not given the posterior probabilities, it is still possible for us to derive them using the Bayes theorem, as long as we know the conditional probabilities. To derive the posterior probabilities, we need to follow the following steps. For step 1, we need to multiply the prior probability to the conditional probability to get the joint probability for each state of nature. For step 2, we add up all the joint probabilities and the sum is called the marginal probability. And step 3, we should divide the joint probability by the marginal probability to get the posterior probability. Let us now attempt to solve a problem regarding the computation of posterior probabilities so that we can fully appreciate the steps involved in doing so. So once again, assume that we are given only the prior probabilities and conditional probabilities. We will also construct two tables, one for favorable and another for unfavorable. We will write down all the given values. For prior probabilities, in this case, S1 is 80% and S2 is 20%. So we write down here 80% for S1 and 20% for S2. For the conditional probabilities, these two pertain to favorable because we have F, and these two pertain to unfavorable because we have U there. The probability of F given S1 is 0.9. The probability of F given S2 is 0.25. The probability of U given S1 is 0.10, and the probability of U given S2 is 0.75. Now, following step 1, we need to multiply the prior probability to the conditional probability to get the joint probability for each state of nature. Under favorable market research, for S1, we multiply 0.8 by 0.9. So 0.8 times 0.9, you will get 0.72. For S2, 0.2 times 0.25, you will get 0.05. And then for unfavorable, 0.8 times 0.10 is equal to 0.08, and 0.2 times 0.75 is equal to 0.15. So 0.72, 0.05, 0.08, and 0.15 are our joint probabilities. Moving to step 2, we sum all the joint probabilities to get the marginal probability. So under the favorable market research, we're going to add these two, 0.72 plus 0.05, we will get 0.77. And then 0.08 plus 0.15, we get 0.23. So 0.77 and 0.23 are our marginal probabilities. 0.77 is the probability of having a favorable report, and 0.23 is the probability of having an unfavorable report. For the last step, we need to divide the joint probability by the marginal probability to get the posterior probability. So under the favorable market research for S1, we will divide 0.72 by 0.77. So 0.72 divided by 0.77, you will get 0.94. And then follow the same steps for the others. Here we have 0.05 divided by 0.77, you will get 0.06. If you're going to add these two together, make sure that you will get 1 or 100%. Moving on to unfavorable table. So to get the posterior probability, you have 0.08 divided by 0.23, and you will get 0.35. And then for S2, we have 0.15 divided by 0.23, you will get 0.65. Add these two together, we get 1 or 100%. So that is how we derive the marginal probabilities as well as the posterior probabilities. Let us now check our answers to see if they are correct. For the marginal probabilities, it is 0.77 and 0.23. Notice that we're able to get it right. For the posterior probabilities, under favorable, we have 0.94 and 0.06, which we were able to get correctly. And lastly, under unfavorable, we have 0.35 and 0.65, which we're able to derive correctly as well. The last topic for Unit 2 is the expected utility approach. So far in our discussions, payoffs are in terms of profits and costs. In other words, these are monetary values. However, sometimes we need to make decisions not just based on monetary values, and this is where utilities come in. Utility is defined as a measure of the total worth of a particular outcome, reflecting the decision maker's attitude towards a collection of factors which may be profit, loss, risk, and many others. Utilities are also most appropriate if payoffs are extremely high or extremely low, that using the expected value approach is no longer meaningful. In using the expected utility approach, we need to assign a utility value to each payoff and use it to compute for the highest expected utility. In this case, we multiply the probabilities to their assigned utilities, as shown in this equation, and sum it up. This is unlike in expected value approach, where we multiply the probabilities to the payoffs. Let us solve this problem pertaining to Rowland Company. Here, we are given 5 investments and 4 potential gains. We are also given the probabilities attached to each gain or payoff. So, if investment A is chosen, there is a 90% chance that there will be no gain. There is no chance to gain $200. There is no chance to gain $500. And there is a 10% chance to gain $1,000, so on and so forth. One of Rowland's investors informs Rowland that he is indifferent between investments A, B, and C, and that Rowland assigns a utility of 10 to a $1,000 gain and a utility of 0 to a gain of 0. We are going to answer 3 requirements for this problem. The first requirement is to calculate the utility values for gains of $200 and $500. We already know that a utility of 10 is assigned to a $1,000 gain, and a utility of 0 is assigned to a gain of 0. So we are going to write it down on the table. Utility value of 0 is assigned to a gain of 0. Utility value of 10 is assigned to a gain of $1,000. And then we need to derive the utility values of gains of $200 and $500. So let X be the utility value of $200 gain, and let Y be the utility value of a gain of $500. Then we write down the equation of multiplying the probabilities to the utility values. So these are the probabilities and these are the utility values. So for example, if you invest in investment A, then there is a 90% chance that the gain is 0. So you multiply 90% times the utility value of 0 gain, which is 0. And then there is a 0% chance that there will be a gain of $200. So you multiply 0% to the utility value of $200, which is X. And then you have a 0% chance that you will gain $500. So you multiply 0% times the utility value of 500, which is Y. And lastly, there is a 10% chance that you will gain $1,000. So you multiply 10% with the utility value of $1,000 gain. So you're going to do the same thing for investments B, C, D, and E until the table will be completed. Next, we need to find the values of X and Y. For investment A, we have 90% times 0, we have 0. 0% times X, 0. 0% times Y, 0. 10% times 10, 1. So let us add 0 plus 0 plus 0 plus 1 is equal to 1. So 1 is the expected utility for investment A. Now it states in the problem that one of Rowland's investors informs Rowland that he is indifferent between investments A, B, and C. That means that A, B, and C should have the same expected utility. So since A has an expected utility of 1, B and C should also have the same expected utility. Next, we need to derive the values of X and Y. We cannot derive X or Y through equating B, since there are 2 unknowns, because there are probabilities attached to x and y. However, we can derive the value of x by equating c, since there is only one unknown, because there is a 0% probability attached to y. So for investment C, that would be 5% times 0, we have 0. 90% times x, we have 90% x. 0% times y, we have 0. 5% times 10, we have 0.5. And then let us equate investment C. So that's 0 plus 90% x plus 0 plus 0.5 is equal to 1. Let us get rid of the zeros and move 0.5 to the right side. That becomes 90% x is equal to 1 minus 0.5. So using algebra, we can derive the value of x, which is 5/9. So we have now solved the utility value of a $200 gain, which is 5/9. Now that we already have the utility value of x, we can now solve for y using investment B. So for investment B, 0% times 0, we have 0. 80% times x, so we just substitute 5/9 for x. That is 4/9. 20% times y, we have 20% y. And then 0% times 10, we have 0. So let us equate investment B. So we have 0 plus 4/9 plus 20% y plus 0 is equal to 1. So we're going to get rid of the 0 and then move 4/9 to the right side. So that would be 20% y is equal to 1 minus 4/9. So use algebra to derive the value of y, and the value of y is 25/9. We now have all the utility values. So for requirement 1, the utility value for gain of $200 is 5/9, and the utility value of the gain of 500 is 25/9. Let us now move on to requirement 2. Which investment should Roland choose using the expected utility approach? Now that we already know the utility values of all the payoffs here, we just multiply the probabilities with these values. We already know from the previous slide that the expected utility of A, B, and C is 1. So all we need to do is to solve for the expected utilities of D and E. For D, we have 0% times 0 plus 80% times 5/9 plus 10% times 25/9 plus 10% times 10. So the answer is 31/8, or in decimal form, that is 1.7222. Now let's solve for E. For E, we have 60% times 0 plus 0% times 5/9 plus 30% times 25/9 plus 10% times 10. So this is equal to 11/6, or in decimal form, that's 1.8333. So if we are going to compare among the 5 expected utilities, E has the highest expected utility of 1.8333. So to answer this requirement, Roland should choose investment E. Why? Because it has the highest expected utility of 1.8333. Let us now move on to the last requirement, requirement 3. Which investment should Roland choose using the expected value approach? All we have to do is to multiply the probabilities to the 4 possible gains or payoffs. So for investment A, that is 90% times 0 plus 0% times 200 plus 0% times 500 plus 10% times 1,000, and that would be $100. For investment B, we have 0% times 0 plus 80% times 200 plus 20% times 500 plus 0% times 1,000, and that equals 260. For investment C, we have 5% times 0 plus 90% times 200 plus 0% times 500 plus 5% times 1,000, and we will have 230. For investment D, we have 0% times 0 plus 80% times 200 plus 10% times 500 plus 10% times 1,000, and that equals 310. And lastly, for investment E, we have 60% times 0 plus 0% times 200 plus 30% times 500 plus 10% times 1,000, and the answer is 250. So among these 5 investments, investment D has the highest expected value of $310. Therefore, we will pick investment D using the expected value approach since it has the highest expected value. For the last example, let us consider a 3-state, 3-decision problem with the following payoff table in dollars. We are also given the probabilities of the 3 states of nature, where S1 is 10%, S2 is 30%, and S3 is 60%. A utility table is also developed. We have 2 requirements. First, which alternative would you choose using the expected value approach? And the second requirement, which alternative would you choose using the expected utility approach? For requirement 1, we shall multiply the probabilities for the 3 states of nature with the respective payoffs per decision alternative. For D1, that is 10% times 100,000 plus 30% times 40,000 plus 60% times negative 60,000. The weighted average is negative $14,000. We need to put the dollar sign since the instruction in the previous slide states that the payoffs are in dollars. Now for D2, that is 10% times 50,000 plus 30% times 20,000 plus 60% times negative 30,000. The weighted average is negative 7,000. And for D3, that would be 10% times 20,000 plus 30% times 20,000 plus 60% times negative 10,000. And you will get a weighted average of $2,000. So comparing the expected values of the 3 decision alternative, we're going to choose alternative D3. We will choose D3 because it has the highest expected value of $2,000. For requirement 2, we shall multiply the probabilities for the three states of nature with their respective utilities per decision alternative. For D1, that is 10% times 100 plus 30% times 90 plus 60% times 0. And the weighted average is 37. For D2, that is 10% times 94 plus 30% times 80 plus 60% times 40. And the weighted average is 57.4. And for D3, that is 10% times 80 plus 30% times 80 plus 60% times 60. And the weighted average is 68. Comparing the three decision alternatives, D3 has the highest expected utility at 68. So we are going to choose D3 using the expected utility approach. And that is the end of Unit 2. If you have any questions, you can post in our Facebook groups or send me a private message. Your assignment is to answer problem 19 in Chapter 13. The deadline is on September 15, 2020 by 10 p.m. It will be available to answer starting September 3, 8 a.m. Please follow the instructions in submitting your assignment. Please don't forget your academic obligations by answering your post-test, submitting your assignment, and participating in the discussion boards on or before the deadline set in Canvas. Have a nice day!